Yeah, so good morning, everyone. Let's just get started. So, before we start discussing about some of these topics, I just wanted to, say a little bit about some of these terminologies that are commonly used. Like if you have read, if you've started reading the textbook or even the lectures of CS 188 lectures, or even the projects that you're working on, you might see some strange things like fringe. Okay, so I've not used that terminology at all. So, what is usually referred to as a fringe is just a set of partial plans. Okay, like we are doing these search problems. So, anything like, so whatever you push into your stack in the case of DFS, or in BFS, whatever is there in your queue is a collection of partial plans, right? As you go along, so you decide to explore some state, and then you keep doing this. So all these, this sequence of actions which are not yet reaching the goal, but it's a partial sequence. That is what is referred to as a fringe. Okay, so in terms of implementation, when you see something like a fringe, when you see a reference to a fringe, you can think of it as also the particular data structure you use, because all the partial plans that you are considering exploring, you will find it in your data structure. So either the stack or the queue, you will find all these partial plans. So that is what is referred to as a fringe. Okay, so I have not used that terminology so much in this course, but maybe that's something you should know, because if you're reading some of these textbooks, they might refer to it as fringe. Okay, so that is one thing. And another thing is, the textbook. Okay, so in the beginning, I mentioned that the textbook has a lot of details. So this is something about these details. So you will see something like a graph search and a tree search. Okay, so you'll see two different things. So what they're just saying is that graphs, we defined two things, right? Like this state space graph, and we also define the search tree, right? So you can do your DFS assuming that your graph is the state space graph, or you can do a DFS or BFS or any of these algorithms on the search tree. Okay, so there are two things, but so based on whether you handle these repetitions, like the main difference is that in a search tree you have repetitions, right? States can appear multiple times. So if you don't handle this, then there are some issues in the search tree. But whereas in the graph search version, we are explicitly accounting for visited states. So in that sense, I didn't see much of a point in, like when I tell you, I didn't feel like I should distinguish between these two. For all practical purposes, you're going to use whatever the state space graph is, and the algorithms are written for that version. Like you keep track of whatever is visited, and then you make adjustments. Okay, so in the search tree also you can do those adjustments. So it's not like hard bound that if it's a search tree, then you don't track the visited nodes. No, there's nothing like that. Okay, so in that sense, these are equivalent. So I've not, delved on these two different versions of the search algorithm separately. Okay, and I think honestly there is no need to distinguish that. But I'm just telling you so that when you read the textbook, that there are these two versions that they talk of. And similarly, these metrics that we saw yesterday about completeness, optimality, and time. I mean, mostly time and space complexity, those things remain the same, but the completeness aspect, that can change for the search tree version. Okay, because if you don't keep track of whatever nodes you have visited, then sometimes you might end up in loops. Okay, such issues are there. But anyway, for us, like you can always, we're all computer scientists, right? And you can write efficient implementations to take care of these. Okay, so I just wanted to highlight these aspects when you read the textbook. Okay, so okay, so any questions from yesterday, yesterday's class, or are there any doubts or something? Is everything clear? Okay,
Yes,
so
ma'am.
yes, okay. Cool. So what we did so far was the search algorithms. We did Bfs and Dfs, and we did some analysis. And for this analysis, we really used the search tree. Okay, so that was easier to think of in terms of the analysis. Now, in the last class, I wanted to actually show you some illustration of how these algorithms work. You will see it in your labs also, but this is just to give you some idea. So let me just show it on the in the Pac-Man space itself. So as you can see, I've been playing a lot of games, but shouldn't be doing that, right? It's not good to play too many games. So let me just let me just run the version that I've coded for Pac-Man. Play this open maze layout. And is it minus A? Okay, it's BFS. Let's do DFS first. So this is a game in which the objective here of Pac-Man is to go from, it started from the rightmost corner and it had to reach this food particle, which is in the bottom left. Okay, so the path, this is a run of DFS. Okay, and you can see that the path it's taking is so longish, right? So are you able to see the screen properly?
Yes, ma'am.
Yes, ma'am.
Yes.
It is visible.
It's visible. Okay. So this is the thing, right? Like maybe I'll just run it once again so that you can see. I'll maybe run it with a smaller frame time. Yeah. So you see, it's there's also some color coding here. So there are some things which are red and the shades gradually reduce. It's getting darker and darker in some parts. So what this means is whatever is shaded is the part of the the entire region which is explored by DFS. So here the states are just these locations. So each location corresponds to a state, and maybe there is some more information about whether there's a food particle or not. Okay. So if you see here, like all this entire region is also explored in DFS. Okay, and in particular, what it's showing you is the path that DFS has opted, the final plan that DFS has found. Okay, and here you saw that it started in this way. It went, and then it did a. It was doing a lot of loops. So now again you can see that it's going towards the wall, and then again it's going to go down, and it's taking a right turn. Okay, so this is kind of a longish path, and this is kind of a characteristic of DFS, right? Because it's going deep and deep and deep till it finds a goal. Okay, so that's something. So whenever it found a goal first, it stopped. So it so happened that the part it explored was this longish plan first, and unfortunately, that was unfortunate for us, and so it was a longish path. Okay, so I will just close this one. So anyway, you get the picture. It does a lot of loopy turns, and even here it does loopy turns. Till the very end, it's doing loopy turns. Okay, so and yeah, the cost it had was something like 298, so it was a long path. So now let's just see what BFS does. So I will just run it first quickly so that you can see. So here you see it came directly down and it quickly went. Okay, so let me just do it a bit slowly. Yeah, so here also, if you see in terms of the number of states which are explored, it has done actually quite a lot of exploration, right? It's explored all this part, and later on it's explored this part, some of this part, and almost the entire grid it has explored. Okay, but final plan that it comes up with is it's been able to identify a set of the shortest path. Okay, so that is what we have seen. The BFS finds the shortest paths. Okay, so this is something I thought was interesting to absorb some of these ideas. Okay, so I will maybe just close this. So here BFS finds the path of length 54. whereas DFS has what did I do? Okay, I ran BFS twice. Okay, so BFS has found a path of length 54, whereas DFS found the 298. The length of the plan was 298 nodes, so that's clearly suboptimal. Okay, so this is the difference between these two modes, and let's. Yeah, so just yesterday we were analyzing all these issues about the time and space complexity and so on. So let's just quickly just recollect that. So I'm just going to write BFS and DFS, and there are three things. So both are complete, so you're guaranteed to find a goal state. Now for BFS, we have, let's see what the space complexity is, the time complexity, and whether it's optimal. Okay, and some things we had was. So what we said was B is the branching factor, okay, in the tree, where at each node you can have B children. Okay, so you can think of it as those are actually boils down to the number of actions. Okay, so B is actually the number of actions that you have, okay, in each node, and you have say let the depth of the search tree be D. So depth of the search tree. So the worst case is when the goal is in at the depth D. Okay, depth of the search tree. Okay, so what was the space complexity for BFS?
B to the power D.
B to the power D, right? So order of B to the power D. And for DFS, what was the space complexity?
O of B into D.
B times D. So this was a stack and this was a BFS was a queue. And what about the time complexities?
B to the power D.
Yeah, for both, right? So both had order of B to the power D. And in terms of optimal, which was optimal? So optimal in terms of the length of the actions in the
BFS.
plan. BFS. Yes, BFS was optimal and DFS was not optimal. Okay, so here if you see this comparison, you can see that there are some good things of both these algorithms, right? For example, this is something nice in BFS, that it's giving you an optimal sequence of actions, whereas that's not the case in DFS. Now, in terms of time complexity, the worst case time complexities both are similar. But in terms of the worst case space complexities, DFS is much better, right? So order of B times D versus order of B power D. So you see, like, there are good things of both. The natural question that we ask next is, can you have an algorithm which combines these benefits? Okay, so you want order of BD space complexity, but yet you want optimality. You want an optimal sequence of actions. Okay, so can this be done? So that brings us to the next variant of the search algorithm. So what you can do is you can maybe adapt DFS. So can you adapt DFS? So the depth first search, can you adapt it so that it is optimal? Okay, so that it's optimal. Okay, so that's going to be the next, I'll talk of this for the next few minutes. And so what is the issue? Like what happens in DFS that makes it not optimal, right? So if you think in terms of the search tree, so what you have is a whole lot of nodes, and it's going on, and there is a goal here, okay, and maybe there is a goal somewhere here, okay, which is actually this is the optimal one. It's more shallow, but what DFS is doing is it's going all the way to the node. I mean, all the way from the start to the root, and it's giving you this. Okay, it's giving you this plan, but instead, can it give you this plan? Okay, so that's what you want for it to be optimal. So how would you do this, right? Any thoughts on how you can do this?
We keep running. Like here, what we are doing is we are returning the first plan that we find. So instead of that, we keep a track of the smallest plan till now and traverse the entire tree. Like till
Right.
all the
So
nodes are visited.
right. So the smallest plan till now, it could be that you will end up seeing this the first, right, in DFS. So this may be the first one that you see, right? So then you will never see this plan, right? This one you are never going to see, right? So that's the issue that is there here. So what you can do instead is, if you can somehow behave as if the tree ends here, right? This is the shallowest node. Suppose the tree was going to end here, then you would DFS would also find this goal, right? It needn't have to go all the way down. Right? So that's the idea essentially. So what you do is, this is a method called iterative deepening. So iterative deepening. So what you do is, you have to cut off the tree at some point, but the issue is you don't know where to cut it off, right? Because you don't really know beforehand where the shallowest goal is going to be. So what you do is you start from here. You keep a cutoff in the beginning itself. So you say that, okay, your tree is only this much, so this much only you're going to explore. So the first node. So is that a goal? So now you see that it's not a goal. So, okay, so what you do is you abandon this and again you do DFS. But now what you do is you keep this as the search tree. Okay, so it's as if you are making your search tree very small. So next stage is this. This is the modified search tree, and you start from here again. You start from the root and you do a DFS on this space. Okay, this is not very hard to implement. In your DFS algorithm, you can just keep track of how many action sequences you have explored. Okay, and the moment you cross this number, you just say that, okay, this is the end. You're not going to explore this node further. It's as if this node doesn't have any children. Okay, so now you will search. I mean, you'll do a DFS on this part of the graph, and then if you found a goal, you will stop there. Okay, if not, what you will do is again you will increase the maximum depth by one more, and now you will do a DFS. So here you will do all this. You will explore this plan, and I mean, starting from the leftmost, right? That's very loosely the leftmost plans, and finally you will reach this goal state. Okay, and then you will just stop the process, and you will not proceed even further. So in this manner, when you do it, what happens is, if the shallowest goal is at level S. Okay, so let's shallowest goal at level S. Okay, if it is at level S, then what it will do is, it's like S times you will do DFS, right? I mean, on different graphs, of course, but you repeat this process S times. And so this, what would be the space complexity then? Can you tell me? I hope the algorithm is clear to you all. Are there any questions on the
S
algorithm?
into B.
S into B, order of S into B, right? Okay, so the space complexity is order of B times S. Now, what about I mean, it is optimal, right? It is, so you are going to get the shallowest goal first. So in that sense, therefore, you have ensured that it's optimal. Space complexity is order of B times S. Now, what about the time complexity? What would this be? So I hope the algorithm is clear.
Previous complexity into D.
So the previous complexity, so what is that?
B to the power D into D.
So you're saying it's B to the power D times D, or B to the power S
Yes.
times. Okay, so how do you get this?
Ma'am, in the worst case, S will be equal to D, right? So
Right.
shouldn't it be B to the power D into D?
Yeah. So the shallowest goal is at level S. So that we are assuming that, this is given. Okay. But there's one thing, right? You're doing a lot of repetitions of DFS, right? Like you're doing multiple runs of DFS. So at each depth, so at, when the depth limit is 0, So let's just write it here. So depth limit when it is 0, what you will do is you will have DFS just on the root node. Okay, so the complexity here in terms of number of nodes, let's just say number of nodes visited, that's going to be 1. Okay, when the depth limit is 0, you have 1. Now, when the depth limit is 1, you're going to have this part, right? This is the next set of, this is the next tree, the next limit, and so this is the tree you will explore. And here you're going to have, B square, order of B square expansions, right? And when the depth limit is 2, you're going to have order of B cube, right? So the third level also comes in. So there's this additional step which is going to come in, right? And finally, at level S, you're going to have B power S. And see, these are going to get repeated. So the first one, you're going to see the, at depth limit 0, there's 1 node, and that is going to get visited at every run of BFS. And that will get executed about S plus 1 times, right? Because you will do DFS about S plus 1 times. Okay, and so the 0 level node that you will end up, so this is the number of times that you do DFS, number of times the node appears. So the nodes appear in DFS. These are multiple runs of DFS that you do. So the number of times the nodes appear in DFS across multiple runs. Okay, so the first one appears S plus 1 times. So at this level, you're going to get S plus 1 times. Now, in this level, it's going to come S times, right? So it will come when the depth limit is 1. When the depth limit is set to 2, you will see all these nodes. Depth limit is 3 also, you will see like that. So this level, you will see it S plus S times. Sorry, you'll see it S times. At level 2, you're going to see it S minus 1 times, and so on. Till finally, you will see this 1 time. Okay, the last level is where you are going to stop, and that is going to get traversed once. Okay, so there is this repetition that comes up. So in short, what is going to happen is the time complexity is just all of this multiplied and summed up, right? So it's overall what you're going to get is, S plus 1, right? Plus, so this had to be B, right? I think I made a mistake here. So this is B. So B square, and so on up to B power S. Okay. So S plus 1 times 1 plus B times S plus B square times S minus 1 plus so on up to B power S. Okay. So this is going to be essentially the time complexity. Now, how do you simplify this? One possibility is, you can use something from these infinite series. So you'll get something like this, B power S times 1. So that's the last term, plus maybe the previous one was 2. What was it? B power S minus 1, right? B power S minus time 1 times S. So 2 only, right? Yeah. So this is this plus 3 times B power S minus 2, something like this you will get. And you could actually replace it with, an infinite summation. Okay. And you will have to do some simplification here. So this is something I will leave it as an exercise for you guys, because I think you'll be familiar with infinite sums. And so you have to use some recurrences here. And finally, what you're going to get is again order of B power S. Okay. So try to do this as a homework. Okay. Have you all done a course on real analysis? CS students, have you done a course on real analysis? Okay, you're all very quiet. I need a yes or no.
MNC students have.
MNC students have, right? So CS, I guess maybe you haven't done it, right? Okay, so anyway, there are some things which will come in here about, interchange of limits and all that. So that is something that, it's a very useful thing to do real analysis courses. Okay, so if at some point of time, if there are some electives, which look at real analysis, that's going to be useful because all these analysis will have that. Okay, so MNC students, I think you are already ready to solve something like this. But anyway, for the rest of you also, you will be familiar with these infinite sums, right? Infinite series, like from your 12th standard, you would have looked at some ways to simplify this, but maybe you would not have gone into all of the details, like how because there are a lot of limits coming in. Okay, so anyway, so I will leave this as a homework for you to finish, but I hope this idea has been clear. Are there any questions on this algorithm?
Can we do it in a different way, like the time complexity part? Like
You want to do?
for a
Go ahead.
particular complete binary tree, the number of
Mm-hmm.
nodes it has is 2 raised to the power d minus 1
Mm-hmm.
for a complete binary tree. So let's say for level 1, we have
Mm-hmm.
2 power 1 minus 1, and for level 2, we have 2
Mm-hmm.
power 2 minus 1, and so on.
Mm-hmm.
And if we take the summation of that, then I think we arrive on same time complexity.
Yeah, so the idea is essentially the same. So one thing is these are not going to be binary trees. They're going to have like B branches. Okay, but essentially that what you said is the same idea. So you take each level and you see how many times you're going to cover those levels. Okay, because
Yes,
you're
and
doing
like how many nodes are there in a particular depth for a tree?
how many nodes are there in each level times the number of visits you do. Number of times your DFS algorithm visits.
No, ma'am,
Right?
I didn't like multiply them with the number of times because it automatically adds up. If you if you always take complete tree,
Uh-huh.
so it so the like add up inside them
Yeah,
uh,
what you're saying is right, but you also have to account for the fact that the same tree gets visited multiple times, right?
yes,
Because you
right.
start, right? So that is also something you have to take. Yes, you're right that you have each. You can take each tree, and sum it up. But you also have that. This is getting visited more times. The root will get. There'll be multiple versions of DFS which will visit the root. Okay,
Yes,
and there'll be multiple versions, multiple times you're running DFS to run the next level, and so on, right? The last
yes.
level you will cover it only in the very last time that you run DFS, right?
Uh, okay.
Sahil, it's not clear. The algorithm, is it clear or no?
Yes, ma'am, this is clear. Like this is clear to me.
It's clear. So the steps are just this. When the root node, you will just visit it. Like first time, you will assume that the tree is only this much. So let me just write it. Maybe others also have some confusions here. So the first time. So this is first time you run DFS. So it's as if this is the tree. Okay. Now, in the second time, you didn't find a goal here. So what you did is you did one more DFS, but now you did it with this, okay, with this tree. So there are B branches. Okay. Now you still didn't find the goal. Now what you're doing is all this tree is already there, the second tree. So this is T1, this is T2 and T3. So in the third iteration, you have T2. So this part is T2. And additionally, you have one more level. Okay, so that's what is going on, and this will go on all the way till TS. Okay, at depth S, you will have this will be TS minus 1. Okay, that's going to be there, and plus you'll have some more nodes here. So you will do a DFS again for this whole tree. So it's a repetition that's coming up. So all these nodes, this TS minus 1, you would have already seen them in the S minus 1 titration, but you will again see them in TS titration, as you try to reach these nodes. Okay, so perhaps there's some optimization you can do there and try to reduce it, but this is a naive implementation of this iterative deepening idea. Okay, so that's why when you account for the time complexities, you still have to account for the number of times you visit. I mean, there are these many iterations of DFS that are happening, and within this, how many times do you visit each node, right? So that's what you need to do, and that's why we have this kind of an analysis. Okay, is this clear? Are there more questions on this part?
My God.
Ma'am, I guess he meant like instead of taking the extra notes, he took the notes of all the tree each time at each iteration.
Yes, at each iteration, yeah. So the analysis times you can do it however you want. Like you can also take each level and see how many times you visited, or you can take each of the subtrees and see how many times. But that you have to be very careful there. If you see how many times T2 was visited, then T2 appears also in T3, right? It comes up there. So you have to be careful.
We can still take the whole tree. Like each time, whatever tree we visited, we will consider all the nodes. So that will.
Yeah, you can do that, but then you should also ensure that when you take, for example, T3 and T4, right? There are some nodes which are coming common in both T3 and T4. For example, now T2 comes up in T3 as well as T4, right? So you just have to ensure that you don't do overcounting also. Okay, so that's something you have to be careful of. But the interesting thing of this algorithm, the interesting feature is that even though you're doing all these repetitions, finally, in terms of order notations, you're still going to be in order of b power s. Okay, the shallowest node is at level s, and whatever the time complexities in terms of order notations, asymptotic notations, it's just going to be b power s. The reason is that in the last level you're going to have b power s nodes, right? So the last level is this level you have b power s nodes. Okay, now all these nodes put together and ts minus 1, if you put those together from the start till s minus 1, still it will be less than b power s. So that's the reason. So the last level is always going to be dominating the time complexity. Okay, so that's the intuitive idea, but to see it more concretely, you have to solve this summation, this infinite series. You have to solve.
We can solve it
Yes.
by using AGP.
Yes, AGP also you can do. You can use whatever techniques, but just remember like how you get this solution for the infinite summations, right? I mean, of course, you now know the formula for this infinite summations, but what I'm saying is, how did we get that formula for this infinite summations? There are some issues there with respect to limits. That is something, I mean, as you study more and more, you will pay more attention to these more fundamental aspects as well. Okay, so that is something that doing something in analysis would help. Okay, but you're right. The essential idea is to use to reduce this infinite summation. You can reduce it to a closed form expression, and then when you simplify it, you get this b power s. Okay, good. Any other questions, thoughts? Okay. Fine. So I hope this has been clear. Many of you are quiet. So please ask, okay, if something is unclear. Okay. So maybe now let's. So this is about the case when we didn't assume anything like costs, right? All actions were considered equally expensive. So suppose you had this notion of costs, right? So if you had costs for the actions, then what would you do, right? So in that case, is BFS still optimal or it's not optimal, right? That's the question. So maybe I will just maybe draw one example for a state space graph, and we can just see it with that. Okay, so I'm gonna take something like this. this is 80. This has a cost of 80. This action has a cost of 97. And this is the goal state. And this action has a cost of 101. And from D to G, there is a cost of 211. Okay, so this is the graph I'm considering. So yeah, this is the start space, the start state. So this is the start. Okay, so let's just write the tree for this. So you're going to start in the state A. So let me write it as A itself. And so there are two options here. So either B or D. So B has B further you can go to C and G, or you could just go from D to G. Okay, so this is the search tree, and there are two ways of reaching the goal. So either through this or from here, right? The two paths. So here, this is A to B. So this was 80. This is 97, 101, 99, and 211. Okay, so if you opted for this plan, what is the total cost of reaching the goal? So the sum of these two, what is it going to be?
310.
310.
310, right? This is the total cost. And what about this one?
278.
278. Okay. So, so you've seen Bfs and Dfs. So Bfs was optimal, right? For when you have like all actions were equally expensive, and it's giving you the shallowest node. So, but here what's going to happen is Bfs will choose this one, right? Because that's the shallowest node, right? But the cheaper one was this, and this is what you want. Okay, you wanted this one, but BFS gave you the more expensive one. So how do you take care of these kind of situations, right? How do you keep track of the costs?
Ma'am,
Okay.
we can use a priority queue or something.
Yeah, exactly. So that's exactly the next algorithm. So which is called uniform cost search. So what you do is, instead of using stacks or queues, what you use is a priority queue. So uniform cost search. So priority queue is the data structure you use. So all of you remember what is a priority queue? Does everyone remember? What are the operations? Yes.
Yes, ma'am.
Okay. What are the operations in a priority queue?
Push, pop,
Let's.
Push, pop,
top,
top,
size,
Okay. So push, pop, and
top and
Move up.
size,
top.
Top,
and size.
size,
Size. Okay. So what does size do?
Count that number of elements present in the queue.
Okay. So count the number. So this is a bit different from the notations I'm using. So that's why I'm asking you to tell me what you have seen in your course. So, and what is top?
It gives a front element. If you are using maxip, then it gives maximum element, or if you are using min, it gives minimum element.
Minimum element. Okay. So let's say we are using the min version of the priority queue. Okay. So this top is going to give you the minimum element. Okay. Fine. And what is pop? What's the difference between pop and top?
Pop removes the top element.
Okay, so it removes the topmost element. So removes the min element and gives you the remaining. Okay. And pushes the usual thing, it inserts.
Add
right?
the element.
Okay, inserts a new element. Now, there's also an update operation, right? So you can also update the priority. So when you push in, what you do is you will push the element as well as there's a priority. Right, so there's a priority which will decide how you pop. So the min element, the min is with respect to a priority measure, right? So when you push in a new element, you also insert the priority, right? So now you can also do an update operation, right? So this is update the priority of an existing element, right? Do you remember this one? This is something you saw.
Ma'am, actually, like in C++, I think like update happens along with push only. Like
Okay. So, right, fine. Yeah, so you can combine these two implementations together into one, right? So push and update. So it's instead of insert alone, you can also do an update. Okay, so let's maybe just do it that way itself. So I just wanted to make it a bit explicit because these are some operations very specific to priority queue. So insert or update priority of element. So it's either you insert a new element or you update its priority. Okay, so these are the operations that we have. So yeah, so this is going to be useful for this uniform cause search version. So what you will do is like you do BFS, it's the same technique, but additionally you will also insert the overall cost till that point. Okay, so the priority here is the overall cost. So priority of state, let's say of any state is the overall cost from start to that state. From the start state, so let me call this A, okay? Overall cost from the start state till A. Okay, for any state, this is what is the priority. So let's just see one run of this, how it will work. Okay, so I'll just move this down. Okay, so what you will do is initially the queue is just going to have the start state. So it's A, and so the overall cost so far is 0. Okay, so this is going to be in your priority queue. And yeah, here you also need the actions, the sequence of actions. So I'm just not writing it for now. So that to avoid some clutter, but in your implementations you can also insert the sequence of actions. So these arrows are the actions, right? You will have a label there, so you can also insert that. Okay, so now A0, that was what was inserted. And so the next thing is you remove the cheapest element from your priority queue. So there's only one element here, that was 0. So you remove that, and now you say that A has been visited. Okay, and the next this you have two options, B and D. So you push both those. So B has a cost of 80, and D has a cost of 99. Okay, so these are the two options. Now what do you do? So there are some elements. So this is the first iteration, this is second iteration. So here now you will remove the cheapest element. So that is this one. Okay, so what you will have in the queue is you have D99, that is still there, and you will mark B as visited, and then you will push B's children, right, or B's neighbors, so the outgoing neighbor, so that is C. And here the new priority is actually going to be the sum of all this. So you removed B with a cost of 80, so you need to, the priority of C is going to be 80 plus this 97, right? So what is that going to be?
174.
177, right? Okay, so now okay, so all B's children have been pushed in. So now the next iteration is going to look at removing D. Okay, so because D is now the cheapest, so D will get removed and you will mark D as visited. So the next step is to, you'll have C177. Okay, and now the child of D is the goal state. And what is the cost of this goal state now? So D had 199 plus 211. What is the cost?
310.
310. So this is actually the bad path, right? So remember one thing. So now you've pushed it into the queue. So one very important feature of uniform cause search is you don't, at this stage, you shouldn't say that you have found the goal, because this is an expensive goal, right? And maybe later on you will find something cheaper. So let's just see that. So now the queue has these elements, and the cheapest element here is C. Okay, so C is the cheapest element. So you pop that one out. And so this is visited. So what you're left with is, so you had to start with, you had now a goal with 310, but now you see that you're going to reach the goal again, but with a lesser cost. So what was this cost now? The new cost for the goal is 177 plus this 101. 278, right? So what you will do is you will update this to have 278. Okay, so 310, the cost lowered, right? And so this is what is there in the queue now. Now in the next iteration, what are you going to do? You're going to pop from this queue. So there's only one element, and so you will pop that. So now you've reached the goal. So the queue is empty, and you return. So goal found. Okay, so at this stage is the goal has been found. Okay, so now you see that this is a very important step where that the algorithm is the same, but instead of identifying a goal state when you push elements, you identify the goal state when you have popped an element. Okay, so that is a very crucial difference. Otherwise, if you don't do that, like, you will not find the cheapest path to the goal. Okay, so I hope this algorithm, the way we executed it was clear. Are there any questions on this? Okay, so maybe in the little time we have, maybe let's just formally write down the algorithm. Okay, okay, fine. So here, as usual, what you will do is you'll have a visited list, which is empty. And you have, now it's a priority queue. So priority queue, so this is, let me call it queue itself. And initially you push the start state. So you have start with a priority of 0. You can push in, you also have to push in the other actions. Okay, so I'm just not saying that for now. Okay, so now what you do is, while the queue is not empty, what do? You take the top element. So let us say the current state and the current priority. Let me call it current cost. Okay, the cost so far. So this is, you take you pop an element from the queue. Okay. So now here, if you found the goal, if the current state is equal to the goal, what you do is you just return the cost, return the current cost, and also the sequence of actions. So this you have to also push it into the queue. Okay, so I'm just not writing it explicitly. Okay, so now you know how to do this, right? In the previous Bfs and Dfs, we have done this step. Okay, so if you found the goal, you return it. That's it. Otherwise, what you do is you mark the state as visited. So visited dot append the current state. Okay, and then what you do is the rest all remains the same for each neighbor, neighbor of the current state. What you do is, if the neighbor is not visited, so let me call it n. If n is not visited, then what you do is you push this guy into the queue. Okay, so queue, so you also have a new priority, right? So the new cost is going to be, so the neighbor, this action is going to have some cost C. So the new cost is going to be the current cost of the previous node, of the parent, plus this C. Okay, and what you're going to do is queue dot push the neighbor and the new cost. So this will take care of, if it's a new element in the queue, it's going to insert, otherwise it will update. Okay, so let me just write it here. It's either an insert or update. Okay, and this will go on. Okay. So this is the algorithm for uniform cost search. Now I'll just show you one demo and end with this, right? So uniform cost search is great. It gives you the shortest path, but there are sometimes you end up exploring a lot. Okay, so to see that, so this is a demo from the Berkeley course. So what you're trying to do is you want to get from the green state, this is the start state, and you want to go to the red state, that is the goal state. Okay, so the shortest is just this path in green, right? But in order to find that, it's not able to do it soon. It's going to go all around and around and around, and after much exploration, it's going to find this shortest path. Okay, so that is an issue with all these algorithms. Actually, even BFS, we saw a demo, right, that it explores so much around it before finally finding one path, right? So is there something you can do to make it better, right, to reduce this exploration? So that's what is going to be the topic of the next class. So with some more information, so all these algorithms, they don't make use of any kind of information, right, about how far are you from the goal. That information is not there. So if somebody told you some information like this, some heuristics, then can you do better? Okay, so this BFS, DFS, uniform cost search, iterative deepening, all these are called uninformed search methods. Okay, so these are all uninformed search. So what we'll see next is informed search. Okay, so yeah, so I will just stop here for now. And if there are any questions, I'll hang back. Otherwise, yeah, thanks everyone. We'll meet tomorrow.